Um, Great to be here. The title of my talk is sort of slightly different to what was billed. So I've added on this finding Pegasus, leveraging the manifold. We'll make it clear why. I'm Paul Nathan. I'm from University College London. I'm a second year PhD student we've got like a sort of center for data intensive science within physics and astronomy, and super excited to be here today to, I guess, talk about maybe just some thinking that we've been doing about anomaly detection recently. So like the whole thing in 5 bullets, just in case you don't want to concentrate more than the first second or so. But we collectively, there's wide scale use of unsupervised machine learning techniques when performing anomaly detection in astronomical spectra. But all these techniques struggle to a certain extent with high dimensional data, and we've sort of seen that in a couple of presentations already. Hence, we usually choose to work in lower dimension. But dimensionality reduction creates a manifold, which will be model dependent, and hence the anomalies detected using it will also be model dependent. So we introduce the idea here of thinking of anomaly detection models as working as either on manifold or off manifold, and note that they can represent very different things. And then for a given manifold, combining complementary on manifold and off manifold techniques should be able to increase the range of anomalies we detect. Okay, now the full thing. So I guess we all know we're living in this sort of golden age of astronomical spectra, projects like DESI and so on are giving us huge amounts of data, but that sheer volume of spectra means that it can be a challenge to find anomalies. We use unsupervised machine learning anomaly detection techniques, and we use them extensively, but they can struggle with high dimensional data. There was a nice benchmarking study done by Han et al. In 2022, where they took a lot of the sort of commonly used anomaly detection sort of tools on PYOD and scikit-learn. And when they tested them, lo and behold, I mean, none of them was statistically better than any of the others, which is kind of makes sense from a no free lunch perspective. But also when you sort of like dig into the data, you see that none of them perform particularly well on high dimensional data sets. So why is high D a problem? Well, the raw data representation of a lot of things, especially spectra, is often high D because of the way the data is collected rather than reflecting the underlying physics. So for DESI spectra, we're in about something like 7,800 bins. And this unnatural high D representation, it lends us no physical intuition. It's hard or impossible to work with computationally, and means we are afflicted by the curse of dimensionality, which was mentioned by at least one speaker yesterday. So in high D, data becomes increasingly sparse, and the distance between points increases, and points are found more towards the boundary of the space. Conversely, the distribution of these points becomes much more tightly spread. So the concept of nearest neighbors, which is fundamental to many anomaly detection techniques, kind of falls apart. So dimensionality reduction should be beneficial, but like, how do we do it, and is it even meaningful to do it? Well, I mean, Josh talked about this yesterday, which is great. So dimensionality reduction relies on the manifold hypothesis that most real-world high D data sets actually reside closer to a lower dimensional manifold. And this seems to be valid for spectra. There's a nice body of work by a bunch of authors. I've just mentioned a couple there, Yip et al. And Portillo et al., where they did work to show that you can well represent astronomical spectra in a very small number of dimensions. And we can find this low D manifold using linear projection methods, maybe something like PCA, or nonlinear manifold learning, TSNE, which was again mentioned a few times yesterday, local linear embedding, or deep learning methods like autoencoders like Peter was using, or variational autoencoders. But again, the manifold we find will be different depending on the model we use. So linear methods will typically find a hyperplane, nonlinear methods will find more complex shaped manifolds. So how does the manifold affect anomaly detection? Well, there are two main ways of identifying outliers. One is to look for points which are isolated, or in the distribution, or they're extreme in the distribution, or they're in areas of relatively low density. But we know that in high dimension that can be problematic, so we usually transform to a low dimensional, to low D first, and then look for extreme points on that. For the purposes of this talk, we're going to call these on-manifold anomalies. And the other way is to construct a low D manifold, which well represents the bulk of the data set, and then points far from this manifold with high reconstruction error are assumed to be outliers, and we call those off-manifold anomalies. We've already seen the model, the manifold is model dependent. Therefore, the anomalies detected will also be model dependent. And furthermore, on-manifold and off-manifold anomalies are likely to be quite different. If we've constructed the manifold well, then aside from instrumentation artifacts, which could exist anywhere, on-manifold anomalies should represent extremes in our current thinking, and off-manifold anomalies could be where we find new or rare physics. So, okay, we've talked about a bunch of kind of like theoretical concepts here. So let's have a couple of examples now. In a moment, I'm going to talk about some actual DESI data. But first, we've got a slightly simpler example. I thought we'd use horses as a data set. So we're going to start off with like a two-dimensional data set of horse height versus horse weight. So this is kind of where you'd sort of expect them to be, reasonable correlation between height and weight. But let's put on a couple of anomalous points as well. We got these two guys here. So this little guy over on the left is Eohippus, who is like 20 centimeters tall, and he was precursor of the modern day horse. And the big guy over on the right is Samson, who apparently was the tallest horse ever, and he was 2.2 meters to the shoulder. And I think that's a little bit of an exaggerated picture, but anyway, these are our anomalies at the moment. But now we're going to add a third dimension, and this dimension is going to be numbers of pairs of wings. And it's just a one-shot thing, so it's either going to be 0 or 1. And for most of the data set, as you'd expect, they're horses, right? Most of the data set aren't affected by this. They've got 0 pairs of wings. We're going to have one point, which has got 1 pair of wings, and that's going to be Pegasus. All right. Now, let's just assume, because of the curse of dimensionality, we're struggling with 3 dimensions. So we're going to reduce dimensionality. We're going to do that by using PCA. So we're going to find a lower dimensional manifold. And not surprisingly, the lower dimensional manifold we're going to find through PCA is pretty much just going to be the height weight plane. And now we're going to do, and then when we project our points down onto it, most of the points just stay where they are, but the Pegasus point ends up in the middle of the distribution there. Now, so this is kind of critical, I guess. We're assuming here that Pegasus is average height, average weight, but its wings are kind of gossamer light, right? They don't weigh anything at all. So as I say, when it gets projected down, it ends up in the middle of that data set. It's got magical wings, right? That's kind of what you'd expect. Now, were its wings to be heavy, then it would probably end up maybe over to the right a bit and in an area of relatively low density. So if there was some kind of correlation between wing weight and one of the other dimensions, then we might expect it in an area of relatively low density. But as it turns out, it ends up in the area of very high density. All right, now we're going to do some anomaly detection because that's what we're all about. So first of all, we're going to do some on-manifold anomaly detection. We're going to use local outlier factor to try and find points which are in areas of relative underdensity on the manifold. So we find Eohippus and Samson no problem at all, because you can see they're well away from the central distribution of points. But we don't find Pegasus, because Pegasus, as we said, when it gets projected down onto the manifold, ends up in the middle of the distribution of points, and so in an area of high concentration. Now let's do some off-manifold anomaly detection. So now we're going to be looking at the reconstruction error between the original point and the manifold. Now we find Pegasus, hooray, very, very easily, because it's obviously got high reconstruction error from the projected manifold. But we don't find Eohippus and Samson very easily, because they're pretty much on the manifold. So depending on the model you've used and the manifold that you get, your anomalies and all your points could end up on or off the manifold. So here in this, for this manifold, we had these guys as the on-manifold on-manifold anomalies, these ones as the off-manifold anomalies. But all of these are interesting anomalies. In some ways, as I say, Pegasus is kind of new physics, kind of a little bit magical, but I guess all new physics is a bit magical until we got a theory. But Eohippus and Samson, they're kind of interesting points as well. And so by combining on and off manifold methods, it might help us to find all three of these points. All right, let's move on to some like real data. So now we've moved from a 3D example to a 7,800D example. I've got some DESI spectra from the Bright Galaxy sample. I had about 55,000 spectra, and it's split about 60-40 between stars and galaxies. I did a little bit of normalization, some downsampling and deredshifting. There's minimal other pre-processing for this kind of like proof of concept sort of work. So there are still a fair bunch of instrumentation artifacts in there. I then used a variety of dimensionality reduction techniques to form a 6D manifold. So why 6D? I think Peter was using the same as well, but Portillo mentioned 6 dimensions as a pretty kind of sweet spot for spectra. I used PCA, I used a linear autoencoder, which was more of a control because that ought to approximate to an autoencoder and an autoencoder. And then I've visualized those 6 dimensions down to 2 dimensions, as a bunch of other presenters have done using TS&E. Okay, and so this is what I got, these lovely kind of brain type images. So quick aside, the blues are galaxies, the reds are stars. So you can see, as I say, as an aside, you get this unsupervised classification that we saw with, again, some other presenters, and that's why people like dimensionality reduction anyway. But the other thing to say is, so PCA and the linear autoencoder visually look pretty similar. So the manifold we've created are pretty similar, but it's different to the autoencoder. It's not just a rotational thing, they're actually different manifolds. So first thing, to just reiterate that point, the manifold that we've created is model dependent. Then we take one of those manifolds, so we're going to take the PCA manifold, and we're going to do some off and on manifold anomaly detection on it. And for the purposes of this, all we've done is we've just taken the 1% of the total population which are most extreme using either method and called those anomalies. So when I do my off manifold anomaly detections, this is reconstruction error. These are the Pegasus type points. I get these bright blue spots, okay? When I do on manifold, I get these yellow spots. So it's just the obvious thing to say is that on the whole, they're different points. The similarity score between those 2 sets of anomalies is only about 2%. So they're very different points that we're getting. And then when we look at them in combination, we can see that obviously we'll get the sort of superset of those points. So by combining on and off manifold methods, we ought to be able to detect more anomalies. See exactly the same thing when I use the autoencoder manifold. Obviously, the manifold itself looks a little bit different. But again, I get the bright blue points for the reconstruction error method, which is on the left. And then in the middle, the yellow points show the local outlier factor method, which is on manifold. So again, combined, we would get a superset of more points. Okay, that's pretty much it. So the takeaways, unsupervised anomaly detection is model dependent. It's helpful to split techniques, anomalies between on and off manifold. And I guess this is the key point. By combining complementary on and off manifold techniques, we should be able to widen the number of anomalies we detect in high dimensional data. And look, many of you who are using these sort of techniques are intuitively combining anomaly detection techniques anyway because of the inherent model dependence there. But we hope that by viewing the problem from the perspective of the manifold, will actually, I guess, inform those choices a bit better. It's a work in progress. I'll be doing a bunch more in this space. Please get in contact. Shameless plug for